Okay, so in this lecture, we're going to start to talk about force, stress, and strength, which is really building off of chapter 3 of our textbook. And so in this lecture, and at the beginning of a couple of subsequent lectures, we're going to talk about dynamic analysis and then the idea of force, traction, and stress, and then the relationships between stress and strain, and talk a little bit about deformation experiments. So if you remember from the earlier lectures in our class, we talked about how structural geology introduces the physical side of geological sciences and has these three emphases. The first one is geometry, so the shape, orientation, position, size, etc. of some objects, which might be like a fault or a fold or something. And then the second one is motion, so how do we think about the beginning and ending positions and the paths of particles and bodies. And so we've talked about deformation or the change in geometry. So now we're going to move into mechanics and try to explore how we might explain what has happened. And so just as an example of geometric and kinematic descriptions, let's look at something from our textbook. And it's about the Alpine fault, which is a plate boundary that cuts through the South Island of New Zealand. And this text that is from the textbook provides a really useful view of the language that we use when we describe structures. And so let's just read it. The Alpine fault zone originated about 6.4 million years ago and has accommodated 70 to 75% of the total oblique convergence between India and Australia plate, between the Indian, Australian, and Pacific plates, namely about 480 kilometers right-handed strikes of faulting, which ends up to be about 36 millimeters per year, and 70 kilometers of crustal shortening, about 10 millimeters per year. Overall, the Alpine fault strikes 55 degrees, dips about 50 southeast, and the slip trends 70 to 90 degrees. The Alpine fault projects to a depth of at least 25 kilometers. Because the brittle ductile transition is shallow, 5 to 8 kilometers, and the rate of uplift high, about 8 millimeters a year, myelinites, which are formed through ductile shearing, and cataclasites, formed through intensive deep brittle shearing, have been brought to the surface and are faulted atop fluvial outwash fan gravel that's younger than 10,000 years. Even frictional mouth snow glass, produced by earthquakes at depths of 20 kilometers, can now be found at the surface in the form of pseudotachelite. So this picture here is a picture of a rock that has this dark material, very fine grain. That's the pseudotachelite, which is a frictionally generated melt. If you rub your hands together, they get hot, and in an earthquake, the rocks slip so fast that they heat the walls of the fault surface and melt. So this text is a rich and dense language that describes a lot about this fault system in very few words, but mostly it talks about the orientation, so the position and the attitude of the fault, but then also the motions, what's moving, what direction, and a little bit about how fast it's moving. So it just gives us a taste of that kind of description. So what we just talked about was some of the descriptive analysis, where we recognize and describe structures and measure their locations, geometries, and orientations, and a little bit of kinematic analysis where we focus on the motion of materials. So now as we move into dynamic analysis, we're interpreting the motions in terms of applied forces. And so one way we can do this is to use physical models where we simulate earth processes in a controlled experiment. We build intuition about how things work as opposed to actually trying to predict something specifically about the earth, just what kind of gives us the forms and geometries that we see in motions, and then what are the controlling processes and conditions. So let's watch this video. So in this video, we have sand that's been layered, and underneath the left half of the model is a mylar sheet or a plastic sheet that's being pulled, and underneath the other side. And so as we pull, we're sort of applying this force to the bottom of the sand pile, and we move it inward and it piles up. And the idea is that this is an analog for how you might make a mountain belt where we have thrust faults that are sort of stepping outward, kind of accommodating this deformation, and we sort of pile things up in the interior. So this view just shows the same model but from a different vantage, so you can see the surface topography of our mountain range with the folds that might be associated with it. And in reality, we know that this kind of relief would be eroded, and so we might expect a landscape to develop on top of this. And it's quite interesting to study how that landscape might evolve as an interaction between the active deformation and the surface processes. Here's another sandbox model where we're pushing on the side as opposed to pulling along the bottom. But again, we apply some force, and the material isn't strong enough to withstand it, so it changes its shape. So in the mechanical analysis, we try to develop simple rules to explain behavior, and these can be stated usually in symbolic or mathematical terms. So probably the most famous examples from Isaac Newton, who he was an English physicist, mathematician, astronomer, philosopher, alchemist, theologian, who's been considered by many to be the greatest and most influential scientist. And he wrote a book called the Principia, but translated as the Mathematical Principles of Natural Philosophy. And in it, he laid out the idea of the definition of force. So F equals ma, which is one of the most famous equations that we know. So let's spend a little bit of time talking through, sort of in more detail. F equals ma comes out of a couple of laws of motion that Newton developed. So the first law, he said, every body continues in its state of rest or in a uniform motion in a straight line unless it's compelled to change its state by forces pressed upon it. So I think keywords there is compelled. So things just keep the way they are unless you push on them, you do something different. And so the best example is sort of the pool, playing pool or billiards, where we have the force associated with the transfer of motion from the cue ball to a target ball.
And line it up carefully, and remember, level cue and don't move.
So in that case, we had the incoming ball, and it transferred, it's almost stopped, and it transferred all of its force, and which gave motion to the other ball. So the second law is that the rate of change of momentum is proportional to the impressed force and is made in the direction in which the force is impressed. So this is really F equals ma, that force is equal to the change of momentum and that it's a vector, so that it has a direction. So here is putting into mathematical terms that statement. So momentum is mass times velocity. So if we just say, all right, so force is the change of momentum and changes over some time. So we can use simple calculus to say, well, like the cue ball has some mass and some velocity, and it's going at that motion until it hits the other ball. So it very quickly, so in a very small delta t, changed its velocity. The mass stayed the same. So in that sense, we can take say that we could take the limit and say that delta t approaches 0, so we get this dmv dt, but mass isn't changing, like the mass of the cue ball doesn't change. So it's really the change in velocity over time that gives us acceleration. So in the case of the cue ball, it decelerated. It went from a high velocity to basically 0 over a short amount of time. So change in velocity with time is simply acceleration, so we have F equals ma. So the definition of these different variables is shown below, and sometimes we try to draw a little hat or some kind of symbology indicating what's a vector and what's not. So velocity has a magnitude and direction, same with acceleration. So then let's just take this apart a little bit and think about, well, okay, what's the difference between mass and weight? And so mass is something that doesn't really change unless you're going close to the speed of light or something. But for most of our studies in structural geology, we don't worry about motions that are so fast. And so then we assume that mass is just to measure the amount of material in a body, whereas the weight is different, and it's the force due to gravity acting on a body. So we might compare how much a liter, so we know if we have a liter of water, what's its mass, and then how much does it weigh on the Earth versus how much it weighs on the Moon. So let's look, sort of take force apart. So if F equals ma, we can say, all right, well, that's mass, and acceleration is some length divided by time squared, because it's length over time, which is velocity, but then again divided by time, because it's the change in velocity over time. So in the SI units, the metric system, commonly accepted units are kilogram for mass, meters for length, and seconds for time. So if we have kilogram mass per second squared, that's the unit of force, which is a Newton, or we use N. So if we come back to our question, a liter of water is 1 kilogram everywhere. It doesn't matter where you are in the universe. It has a mass of 1 kg. However, it does matter where you are for the weight. So on the Earth, it weighs force equals mass times gravity. So 1 kg times 9.81 meters per second. So on the Earth, that liter of water weighs 9.81 newtons. But on the Moon, if you go through the calculation again, we see still 1 kilogram of mass, but the acceleration on the Moon is so much lower because it's a smaller body, 1.64 meters per second squared. So on the Moon, our liter of water weighs only 1.64 newtons. So let's think a little bit more about what does a Newton feel like. The best way to think of what a Newton feels like is to think of the bowling. So if you launch your bowling ball, it goes from behind you, your arm, where it's at 0, and you launch it out in front of you and has some rapid motion that you use to send it down the lane. So this is a bit of text from our textbook, but basically the idea is that let's try to calculate this out and say, well, how many newtons does it take to launch a bowling ball? So we need to figure out the different parts. We know it's F equals ma, and so let's think of the velocity change first. So the main thing is that we go the ball, when you start off, it's behind your arm, it's at 0, and then it goes to the release velocity in just a half a second. That's the time it might take our arm to move. And the launch velocity is about 13 to 15 miles per hour. So let's go through the math. We can say, okay, 14 miles an hour is about 6.3 meters per second. But we know it goes from 0 to 6.3 meters per second in a half a second. So our acceleration is 12.54 meters per second squared. Now, we need to figure out the mass, so it's a 16-pound bowling ball. So if we convert that to kilograms, it's 7 kilos. So F equals ma, 7.26 kilos times 12.54 meters per second equals 91 newtons. So that's in a sense, what is a Newton? 91 newtons is the force required to launch a bowling ball. Another important thing about force is it's a vector. Remember, the mass is not a vector, but the acceleration is. It matters which way things are going. So you take this example of this ship. We can have two tugboats pulling on it. Each one applies some sort of force in T1, T2 directions. So the net force is just the addition of the vectors. So T1 plus T2, we have one vector, we put the tail of the next one at its head and kind of add them up graphically, connect the very beginning to the very end to get the resultant force. So let's say we want to talk a little bit more about vector addition. A good way to think of vectors is to take them apart into their components. And so, for example, A here has a certain component in the x direction, AX, and a certain component in the y direction, AY. Same with B. So we can use the sort of head to tail approach for vectors graphically, but practically we just sum their components. So the CX is the x component of the C vector is just the sum of the components of the A and B vectors in the x direction, and same with CY. So let's apply this a little bit more to geological example. So here's a landslide, and it's a mass of rock that's sliding on some kind of more resistant interface. And so we have this 10,000 kilogram block of rock. And we want to know what the normal and shear forces are along the base given the 10-degree dip. So this is just doing a little bit of trigonometry to determine those components. So what do we know? We know that the weight of this mass is that the force vector, which is the mass times the gravitational acceleration, which is going straight down. So we can determine the components. The shear force is the direction parallel to the interface, and the normal force would be the force perpendicular to it. So by simple geometry, we can take this 10-degree dip to figure out that's a 10-degree angle between the total force vector and the normal force component, and use this with our trig to determine the components. So the force vector is 10,000 kilos times that gravitational acceleration. It's 9.81 times 10 to the 5th newtons. And then if we do our trig, cosine of this phi is the normal force divided by the force vector. We end up with 9.66 times 10 to the 5th newtons. And the shear force comes from the sine, and we get 1.7 times 10 to the 5th. So mostly this landslide doesn't want to move because almost all of its mass is holding it against the slide surface. So that's why perhaps if it was a little steeper, it would slide more easily. So the third one of Newton's laws of motion is that it's called equilibrium. So to every action, there's always opposed and equal reaction, or the mutual actions of two bodies on each other are always equal magnitude and opposite in direction. So in this car, sitting here has a certain amount of weight, so that's the force times the force, or the mass times acceleration. But something's holding it up so it doesn't move away, and that's the strength of the asphalt and the road beneath it that's pushing back. So this keeps our car fixed. So it's called equilibrium. So you can say this, well, why don't we fall through the floor? What resists? So we have the sum of the forces. So the sum of all the force vectors, so remember it's directions, not just magnitudes, has to equal 0. So here I am standing on the floor, so I have a certain downward directed weight, force, mass times gravitational acceleration, and what's pushing back is the sort of material, the floor itself, and that comes from the sort of molecular level kind of pushback of the floor beneath me has the interatomic forces that act like springs, and they're very stiff, so it's not like you can usually see the floor deforming, at least in a modern building with a cement floor, but if you think of a house with more of a wooden floor, we know that that floor flexes. So that's the flexing is the sort of finding that even point between the weight of the person walking on that flexible floor and the pushback of the floor as it is warped. It develops some more force to resist motion, and that gives us then equilibrium where we don't fall through the floor. So finally, coming to the big questions of sort of why is this relevant to structural geology, is that we can cast our favorite theory of how the Earth works in terms of plate tectonics as forces and driving and resisting forces. So this is a diagram that shows kind of all the main forces of plate tectonics, and we can think of the F's as the driving forces and then these R's as the resisting forces. And so big sources of driving force for plate tectonics include this ridge push. So the ridges are high and they push down and out. There's the pull of the slab. So this denser material is kind of pulling the slab down. It's also negatively buoyant, so it's a fall into the mantle. And there's also kind of a suction. So sometimes this force comes from this way to sort of push this direction that helps drive the plate down. But there's many things resisting this. There's the resistance of the ridge. There's kind of a bending resistance. There's the obvious kind of overriding plate resistance where we build up a lot of resolved forces that might be released in big earthquakes. There's mantle drag under the continent and so on. So this balance between these driving and resisting forces is what is kind of the amazing thing about plate tectonics, and that's those motions that are reflecting this delicate balance.